Okay, so here we go. We talked about Pythagorean trig functions, and you got to keep in mind that you can find the other two, and the other two are 1 plus tangent squared t equals secant squared t, and t could be x, could be theta, could be whatever, and then cotangent squared t plus 1 equals cosecant squared t. You're going to see me derive this an awful lot until we get used to seeing them, because the permutations of them are used in identities. So if I have tangent squared t, I can subtract 1 and find out that is the same as secant squared t minus 1. Okay, that's just a different version of the tangent 1 plus tangent squared t equals secant squared t. Also, I can say that cotangent squared t is equal to cosecant squared t minus 1. So keep in mind their connection with each other, but you know, it's really kind of interesting. The cofunctions of tangent and cotangent, secant and cosecant, if you pay attention to secant, cosecant, tangent, cotangent, the cofunctions are pretty much the same connection with each other when we're going through this. So that might be helpful to recall them better when we're doing them. But let's use them. Let's get it going. Okay, as we're going through, let's go down here to using the identities. Now, we're going to use the identities first, it's going to seem kind of clunky for us to find some values here as we step through. So this first value we're going to do is we're looking at the idea. Let me get my little bouncy cursor down here. We're going to use the identities, and we're going to find sine theta and cosine theta if tangent theta equals 5 and the cosine theta is greater than 0. So that's the first thing we're going to use. So in order to do this, we're going to go over here, and we're going to say 1 plus tangent squared theta is equal to secant squared theta. Now the reason why I did that is because they told us that tangent theta is 5. Well, I know that tangent theta is 5. I'm going to pop that in. So now I've got 1 plus 5 squared is equal to secant squared theta. Okay, well, I square that and I get 26 is equal to secant squared theta. Okay, I take the square root plus or minus the square root of 26 is equal to secant theta. And now we're talking about finding sine and cosine. So I'm going to find cosine because remember, cosine and secant are reciprocals of each other. And since they're reciprocals of each other, I can now look at this and say, well, plus or minus 1 over the square root of 26. Well, excuse me, let's talk about that so you can see what I'm doing. In my head, I'm thinking this is 1 over cosine theta. Okay, now let's do the reciprocal and find out that plus or minus the square root of 26 is actually plus or minus 1 over the square root of 26 is actually cosine theta. So now we have cosine of theta, and I refer back to the original part of the problem where they said cosine theta is greater than 0. So I am no longer interested in the plus or minus version. I know right now that 1 over the square root of 26, or better yet, if I multiply by the square root of 26 over the square root of 26, I get the square root of 26 over 26 is equal to the cosine of theta. Okay, that's the first thing I was supposed to find. All right, let's make that nicer. Let's talk about the other thing I was supposed to find, and that is supposed to be my sine. Okay, so I'm going to go back and grab the other Pythagorean identity, cosine squared theta plus 1 is equal to cosecant squared theta. And now remember, we're supposed to know that cotangent and tangent are reciprocals of each other. So if tangent theta is 5, cotangent theta must be 1/5. So I put in 1/5, square it, and now I'm going to have 25th, so I'm going to make that 1 a 25th to be cosecant squared theta. So this is 1/25 plus 25 25ths, and I'm sitting at 26 25ths, and this is all equal to cosecant squared theta. Now, remember cosecant squared theta as we're going through here. This is 1 over sine squared theta. And now I do the reciprocal, okay? And so I've got 25 over 26, and I've got the reciprocal, that's sine squared theta. Well, I can take the square root of both sides, and I got 5 over the square root of 26 is equal to sine theta. And now I've got to make it pretty at the bottom, so now 5 the square root of 26 over 26 is equal to sine theta. Now, I've got to remember a couple things as I'm going through. One of the things I dropped as I did this one is after I took the square root, I had a plus or minus. But now I've got a positive since tangent was positive. So although I have those options, I go back up here and I recognize that tangent's positive. They said cosine's positive. So therefore, since tangent positive and cosine's positive, sine must therefore be positive. And this is my final answer for sine. And this is my final answer for cosine. Now going on here, the example 2. Now, the next thing before we get to example 2 is talking about cofunction identities. Remember, I've got angle A, and angle A has a certain sine, and angle A has a certain cosine, but more so, if I look at the cosine of angle B, do you see that sine of A and cosine of B are the same value? Okay, this is important to keep in mind. And it's not just a coincidence. If I look at the cosine of A, and I'm talking about the sine of B, they're the same value as well. And then if I continue on kind of on that ilk and look at tangent of A, and I look at the tangent or the cotangent of B, okay, and if I'm taking on with that and I grab a blue, I've got the cotangent of A and the tangent of B, they're the same value. Now, to continue with that, I got secant and I've got cosecant of A and B, and they're the same value. And finally, I'm hoping that you're recognizing cosecant and secant. Now you're sort of like, maybe this is just a coincidence, but what these are, when I talk about the measure of angle A plus the measure of angle B in a right triangle, they're 90 degrees, okay? And when I'm looking at that, they're complementary angles. That's where our cofunctions come from. Cofunctions that add up to 90 degrees, angles that add up to 90 degrees are considered cofunctions. They're the same value. So if I'm looking at the sine of 30, well, that's the same as the cosine of 60 and vice versa. But even more so, if I talk about the sine of 38, that's going to be the same as cosine of 52. And I would expect you to check that on your calculator and make sure your calculator is in degrees, please. And then look at this cofunction identities. Because if I have 90 degrees subtracting the theta, then the result of that for sine is the same as cosine. And those other co-function values, tan and cotangent, secant and cosecant, works the same way. It's kind of a neat property, but we're going to use them with our identities along with our odd and evens. So let's talk about which ones are odds and which one are evens. And again, sine is still odd, so therefore cosecant's odd. Tangent's odd because it has sine in it. Cotangent's odd because it has sine in it. And the cosines are even because it doesn't have a sine, okay, and the secant has a cosine, so that's even as well. Notice what happens with the value inside. It can come out and it ends up being here, okay? Notice what happens with the value inside. It comes out, that negative comes out on the outside of the function. But when we work with the cosine value and the secant value, we drop that negative value. So that was part of that odd and even thing. So odd functions, it goes to the front, and for our negative b becomes our negative a, or it takes the opposite of our a value, and the negative b's inside a cosine or secant function for our even functions, we just drop them away because of the reflexive, when we reflect things across the y-axis, it's the same wave for cosine and secant. So keeping that in mind, we're going to look at example 2. And I've got the cosine of theta is equal to 0.34. Find the sine of theta minus pi over 2. Well, the first thing I've got to do, I've got sine of theta minus pi over 2. And remember those cofunction identities? Well, they had kind of pi over 2 first. So let's look at rewriting it. So this should be the same as a negative pi over 2 plus, and I should put a theta in here, plus theta. And now if I factor out a negative, and keep in mind what I'm trying to do, this is an odd function, I can do that. And now I can factor that negative out to the front side or the a position in the term. So this is here. Now, this value that I just came up with, and I don't have my cursor in here, so I'll make one really quick. This value that I just came up with, that's one of our cofunctions. And that sine pi over 2 minus theta is the same as cosine theta. And the reason why I'm so concerned about that is check out what I got cosine theta equal to. So now I can substitute, okay, so this is my substitution step. I still have the negative from that other thing, but now I know sine pi over 2 minus theta is the same as cosine theta. So now I'm just going to substitute again. So this is equal to that negative 0.34. And that's my final answer. Okay. Now, if I'm using identities, simplify the expression to 1 or negative 1. Okay, so I'm going to use identities here. Please keep in mind as I'm doing this, I'm going to, understand that cosecant is 1 over sine. So, and also cosecant is an odd function. So when I get this going, as I'm going through here, I know that next step here is 1 over sine of negative x. Now, keep in mind, that's 1 over sine of negative x. I don't quite have them perfect yet, and I'm going to do that right now. I've got 1 over negative sine of x. Okay? So now when I'm in this position, my sines are going to cancel out, or divide out, I should say. And maybe it'd be better to see if I wrote it out more like this. So you saw that they are going to knock each other out. And my value is just negative 1 when they're done. Because cosecant's an odd function, I get to make that move of taking the negative here, and that has got to be that negative there, out to the front side to become there. Okay, so that's why I was able to use that odd function, odd even identity to do that. Going on, I'm looking at some other identities. So now what I'm going to be doing, I'm going to simplify the following trig expressions to a power of single trig functions. Okay, now when I do this, you're going to notice me factoring things. You're going to notice me doing fractions and the whole lot. So if there's something that I do that you're like, what in the world are you doing, Bloom? Just slow me down. But remember, right now the identities we know are Pythagorean identities. So I would write those 3 Pythagorean identities down. The main one is sine squared x plus cosine squared x, or cosine squared x plus sine squared x. Both are either way I do that, it's equal to 1. And the way I presented it was cosine squared, so I'll do cosine, it'll be always referring as cosine squared x. But first thing, I got a cosine squared there, and I got a sine squared in there. What if I factor out a sine x? I'm going to factor out a sine x here. And I've got sine squared x plus cosine squared x. And remember that identity we just did with Pythagorean theorem? Well, I can now substitute the fact that, and I'm going to write it down, the Pythagorean identity is cosine squared x plus sine squared x is equal to 1. I'm going to use this identity. So now I'm going to substitute 1 in. So sine x times 1. Well, that's a sine x, and I am done because I was supposed to simplify the trig expression to a power of a single trig function. Okay, so I got my single trig function in there. So that's going to totally work. Now, every time I do this, I keep thinking about, what's going to happen? How can I do this? And As we go through some of these, pay attention because this is the difference of two squares. So if it was x minus 1 and x plus 1, it'd be x squared minus 1. In this case, it's going to be secant squared x minus 1. Now, keep in mind, we just did one of the Pythagorean identities, and when I'm looking them over, I can derive the Pythagorean identities, and for secant squared, I can just divide by cosine squared x this original. So if I take the original and divide by cosine squared x, and I'm going to just do this so you can see what I'm doing just to remind you. Remember, I take the original and I divide by cosine squared x, divide by cosine squared x, divide by cosine squared x. This is equal to secant squared x. This is equal to tangent squared x, and that's 1. Well, if I'm to subtract that, tangent squared x is equal to secant squared x minus 1. So I can now substitute this for tangent squared x, and I'm done. Okay, that's the extent of my need for that problem. Okay, but I used the Pythagorean identities. This is the identity I used. I derived it right here. So that's the identity I used, and I manipulated it so I could have secant squared x minus 1. Now, in this next problem, I'm kind of doing the same stuff as I go through here. And as I'm looking at this, we're going to check it out and see what we can do about making some adjustments. The first thing I'm going to notice is I see this as I got a secant theta minus 1. Okay, remember 1 over cosine is secant, so I've got that. I got cosine squared theta. Now I plus secant squared, no, secant theta, because remember secant's even, and even functions, I just get to drop that inside. So secant's even, I get to drop that. And then I got cosecant squared theta, which is plus sine squared theta. Okay, so that's first thing. I'm noticing because I've got cosine squared theta here and I've got sine squared theta here. So I've got these two here. I got this one and this one. Well, that's 1. So I'm going to get rid of my cursor there. And I have secant theta minus 1. And I'm going to write this a little slow so you can see what I'm doing. Plus sine squared theta. And somebody's not using enough room. And this is plus secant theta. And now I'm in a position to be able to say, well, this is secant theta minus 1. And this is 1 plus secant theta. And maybe I could have put that in a better position. But when I multiply these out, it's going to be secant squared theta minus 1. Well, I've already seen that secant squared theta minus 1. It's tangent squared theta. Tangent squared theta is my final answer as I step through that. So I was supposed to simplify the trig expressions to a power of a single trig function using the things I knew. And I used this one a couple times. So keep that in mind as we're going through. We're doing example 4. Okay, as we get to the example 4 here, we're going to be working through, and I've got simplify by expanding the trig identities. Just checking to see where we're going here. Okay, simplify by expanding the trig identities. Okay, so I'm going to simplify it. Well, I'm looking at secant x plus 1 and secant x minus 1, and you know, I see that I can totally get it to tangent squared x. And again, I'm using this identity up here. That's what I'm focusing on. So this is going to be secant squared x minus 1 all over sine squared x. Well, secant squared x minus 1 is the same as tangent squared x over sine squared x. And now my next step is to recognize that tangent squared is the same as sine squared x over cosine squared x. And I'm dividing it by sine squared x, so it's the same as multiplying by 1 over sine squared x. And the sine squared x's will knock each other out, and that becomes 1, so I get 1 over cosine squared x. Well, 1 over cosine squared x, that's a secant squared x, because 1 over cosine is the same as secant. So 1 over cosine squared is the same as secant squared x as we're stepping through these. Now, in the next one, we're going to be looking at a couple combinations here, and we're going to be done with our first day. Now, simplifying by combining fractions and using identities. Simplify the following trig expressions to a power of a single trig function. These seem to be overwhelming, but just take them one thing at a time. Think about, hey, how I'm going to get this done, what's going to happen. And again, I'm thinking about those Pythagorean identities, and I want to make sure that maybe you refer back to them or you have them written down. So let's talk about those Pythagorean theorem identities right now. I've got cosine squared x plus sine squared x equal 1, or theta. Maybe I should just leave it as theta, but I've got x's in this next thing, so I'm just going to leave it that way. 1 plus tangent squared x equals secant squared x. And then I got cotangent squared x plus 1 equals cosecant squared x. Keep in mind, these are the things I'm going to use. And now, if you're I'm doing some mental gymnastics here. I see this right here, I see 1 minus sine squared x. Well, that can be created by subtracting sine squared. I can substitute that as cosine squared x. So that's going to be cosine squared x. I see cosecant squared x minus 1, and that's the same as cotangent. So I'm going to substitute those in because it makes it easier to manipulate single things when they're in fractions than things that have been added or subtracted together. So I'm going to go in and substitute right away. I've got cosine squared x all over cotangent squared x. And now keep in mind, cotangent, now I've got cosine squared x, and cotangent squared x is cosine squared x over sine squared x. So that's the inverse of tangent. So now if I rewrite this down in this next line, I got cosine squared x over 1 times sine squared x all over cosine squared x. Well, the cosine squared x's are going to become 1, and my final answer is just going to be sine squared x. Okay, and I'm just going to double check my answer here, and I'm going to reread to see what they wanted me to do. And they wanted me to simplify the following trig expressions to a power of a single trig function. Got it, done. Okay, but please notice what I did to get there. Okay, I started recognizing the Pythagorean theorem identities as I went through. Each time I do them, there's not just this set way of using them, but again, I'm referring back to those three, and I'm going to think about them as I go. So this next one, okay, I'm going to take this half, and I'm going to manipulate the denominator. I'm going to take this half, and I'm going to manipulate the denominator again. On the right side of the minus sign, I'm going to multiply the top and bottom by the cosine x. On the left side, I want to take advantage of the difference of two squares, and I'm going to do and multiply both the top and the bottom by 1 plus sine x. Okay, using my fraction skills to keep in mind what, the order of things. So I'm going to multiply at the top, so I get 1 plus, and I suppose I can distribute that cosine x. So I've got cosine x plus sine x cosine x all over 1 minus sine squared x. So that's my first thing. My other one on the right, I got sine x cosine x over cosine squared x. Now, I'm going to explain why I did what I did. I knew that I could get this here by multiplying 1 plus sine x on top and bottom. And the reason why is because I wanted to combine the two cosine squared x's. So now I can substitute cosine squared x in for my denominator on this side and combine the terms. So cosine x plus sine x cosine x minus sine x cosine x all over cosine squared x. Okay, now these knock each other out. I've got cosine x over cosine squared x, which is just 1 over cosine x, which is just secant x. Okay, so as we're stepping through, you just got to keep in mind, we're just going to work it one way. As we keep going, we're going to use properties of fractions by introducing a factor of 1, a particular good looking factor of 1 to make it work for us, whether it's cosine x over cosine x or 1 plus sine x or 1 plus sine x. But it's not just limited to that. It's just based on what I feel I can get done in the problem. So now this next one, and I'm going to get this one a little bit smaller. So we're going to go and group those real quick and make them smaller and get them out of my way. Now, this next one looks really nasty, but as I'm looking at it, I got to be thinking, hey, you know, I got a cofunction there. So I'm going to use that cotangent thing. That I'm going to get the cotangent beta there. You know, I might just do that right away. But before I do that, I'm going to do a couple things. First, I'm going to make this tangent pi over 2 minus beta cotangent beta. Okay, now remember I was able to do that because of cofunctions. Cosecant opposite of beta becomes negative cosecant beta, because that negative cosecant beta, I suppose I'll write it like that. The negative cosecant beta, it's an odd function. I get to take the negative b and put it on the outside. And now I've got cotangent beta plus 1. Well, cotangent of any value plus 1, looking at that top left, is cosecant squared beta. So I'm going to substitute cosecant, not cosine, but cosecant, sorry, cosecant squared beta in there. Well, what's this doing for me? Well, I've got things kind of substituted in. The negatives are going to be positives now. Cotangent, cosecant, I'm going to switch them all to sine and cosines. Okay, so cotangent beta, remember, is cosine beta over sine beta. Cosecant beta is 1 over sine beta, all over cosecant squared beta, which is 1 over sine squared beta. Now I can multiply the top and bottom, or I can look at it this way. You know, I'm going to combine the top and bottoms and then switch things over. So I've got cosine beta over sine squared beta times, remember, division by a fraction is the same as multiplication by the fraction's reciprocal. So I've got sine squared beta all over 1. My sine squares are out, and my final answer is cosine beta as I finish it out. Now it looked really nasty, but as soon as I broke it down and used the properties, and then, you know, kind of broke those things down into their building blocks of sine and cosine, it made the problem easier. I keep thinking constantly through the problems how I can make the manipulations faster and easier for me. So be patient with yourself. It will come, but you just got to keep plugging it away. We'll talk tomorrow, and we'll see how you guys did on the video. Thanks, guys. Bye-bye.